The National Electrical Code, specifically Article 422.8b4, addresses the grounding of receptacles installed in bathrooms. This section mandates that these receptacles must have an equipment grounding conductor connected to a grounding terminal. This requirement is in place to provide a path for fault current to return to the source, tripping the circuit breaker and preventing electrical shock hazards. Additionally, Article 422.31 of the National Electrical Code pertains to the specific requirements for jacuzzis, hot tubs, and spas. This section stipulates that a listed receptacle must be located within 6 feet of the inside perimeter of the installed product, such as the jacuzzi, and not less than 18 inches from the edge of the product, measured horizontally. This placement ensures convenient access to electrical power for the jacuzzi while maintaining a safe distance from water to minimize the risk of electrical shock. The Texas Electrical Code mirrors these requirements. Section 210.7 of the Texas Electrical Code addresses grounding and states that all receptacle outlets installed in bathrooms must have an equipment grounding conductor connected to a grounding terminal. This provision aligns with the National Electrical Code's emphasis on grounding for safety in wet environments. Furthermore, Section 210.52 of the Texas Electrical Code specifically addresses hot tubs and spas. It mandates that a listed receptacle must be located within 6 feet of the inside perimeter of the installed product and not less than 18 inches from the edge of the product, measured horizontally. Again, this echoes the National Electrical Code's guidelines for safe receptacle placement near water. The #6 solid grounding conductor is likely sized according to Table 250.122 for equipment grounding conductors for branch circuits and feeders. This table provides guidance on the appropriate size of equipment grounding conductors based on the rating of the overcurrent protective device in the circuit. Selecting the correct size grounding conductor ensures that it can safely carry fault current back to the source without overheating or posing a fire hazard. The grounding conductor must be connected to the equipment grounding terminal of the motor using an approved method, such as a screw terminal or a crimp connector. A secure and reliable connection is essential to ensure that the grounding conductor can effectively carry fault current. Screw terminals and crimp connectors are commonly used and accepted methods for making these connections. While the National Electrical Code and the Texas Electrical Code do not explicitly address the connection of the grounding conductor to the shell of the motor, it is generally accepted practice to connect the grounding conductor to the metal shell of the motor for additional protection against electric shock. This practice provides an additional layer of safety by ensuring that the metal shell of the motor is at ground potential, reducing the risk of electric shock if a fault occurs within the motor. In summary, grounding is a critical aspect of electrical safety, particularly in wet environments such as bathrooms and around jacuzzis, hot tubs, and spas. The National Electrical Code and the Texas Electrical Code provide specific guidelines for grounding receptacles and equipment in these areas to minimize the risk of electrical shock. Key requirements include the use of equipment grounding conductors connected to grounding terminals, a placement of receptacles at a safe distance from water, and the proper sizing and connection of grounding conductors. The use of a #6 solid grounding conductor suggests a substantial grounding path, potentially for a larger motor or electrical load associated with the jacuzzi. The grounding conductor size is determined by the overcurrent protection device feeding this circuit, as specified in Table 250.122 of the National Electrical Code. For instance, if the circuit is protected by a 60 amp breaker, a #10 copper wire would be sufficient as the equipment grounding conductor. However, for a 100 amp breaker, a #8 copper wire would be required. The referenced installation involves running the #6 solid grounding conductor from the outside panel through the house and attaching it to the shell of the motor. This suggests that the motor is likely a significant component of the jacuzzi system, perhaps a pump motor. It is essential that the grounding conductor is properly connected to the motor housing. The grounding connection should be made to a designated grounding terminal on the motor, typically identified by a green screw or a grounding symbol. The surface where the grounding conductor is connected should be clean and free of corrosion to ensure a good electrical connection. While the code may not explicitly require connection to the motor shell, it is a prudent practice to enhance safety. This provides an additional path to ground in case of an internal motor fault that could energize the motor housing. When connecting to the motor shell, ensure that the connection is mechanically sound and electrically conductive. This can be achieved by using a suitable grounding lug or clamp that is designed for connecting to a metal surface. The lug or clamp should be securely fastened to the motor shell using screws or bolts, and the surface should be prepared to remove any paint or corrosion that could impede the electrical connection. In terms of grounding methods, there are several acceptable practices. Firstly, the grounding electrode system should comply with Article 250 of the National Electrical Code. This typically involves connecting to a grounding electrode, such as a ground rod, ground plate, or the metal water pipe system within the building. The connection from the panel to the grounding electrode must be made with a grounding electrode conductor, which is sized according to Table 250.66 of the National Electrical Code. Secondly, the equipment grounding conductor, which is the #6 wire in this case, should be run along with the circuit conductors in the same raceway or cable. This ensures that the impedance of the grounding path is minimized, allowing for rapid clearing of ground faults. Thirdly, all metal enclosures and conductive parts of the electrical system, such as metal boxes and conduit, should be bonded together to create a continuous grounding path. This bonding ensures that all exposed metal parts are at the same electrical potential, minimizing the risk of shock. Proper grounding is essential for protecting against electrical shock hazards and preventing damage to equipment. A properly grounded system provides a low impedance path for fault current to flow back to the source, causing the overcurrent protective device, such as a circuit breaker or fuse, to trip and energize the circuit. This rapid clearing of the fault prevents the voltage on exposed metal parts from rising to dangerous levels, reducing the risk of electric shock. Furthermore, grounding helps to protect sensitive electronic equipment from damage due to voltage surges and transients. A good grounding system provides a path for these surges to dissipate, preventing them from damaging sensitive components. To ensure that the grounding system is effective, it should be tested periodically. This can be done using a ground resistance tester, which measures the resistance of the grounding electrode system. The resistance should be low, typically less than 25 ohms, to ensure that the grounding system can effectively carry fault current. In addition to the requirements outlined in the National Electrical Code and the Texas Electrical Code, there may be local codes or regulations that apply. It is important to check with the local electrical inspector to ensure that the installation complies with all applicable requirements. A qualified electrician should perform all electrical work to ensure that it is done safely and in accordance with the code. A qualified electrician has the knowledge and experience to properly install and test the grounding system, ensuring that it provides adequate protection against electrical shock hazards. They will also be familiar with the local codes and regulations that apply to the installation. Improper grounding can have serious consequences, including electric shock, fire, and equipment damage. It is essential to take grounding seriously and to ensure that the electrical system is properly grounded in accordance with the applicable codes and regulations. Remember that electrical codes are in place for safety. They are the result of years of experience and analysis of electrical incidents. Adhering to these codes protects individuals and property from potential harm. Always consult the latest edition of the National Electrical Code and any applicable local codes before performing any electrical work. Grounding systems are a critical component of electrical safety, especially in installations involving water, such as jacuzzis and hot tubs. The National Electrical Code and the Texas Electrical Code provide detailed requirements for grounding these systems, and it is essential to follow these requirements to ensure the safety of people and property. The specific articles mentioned, 422.8b4, 422.31a, 210.7, and 210.52 address specific aspects of grounding and receptacle placement in these environments. Additionally, proper sizing of the equipment grounding conductor, as outlined in Table 250.122, and proper connection to the motor housing are crucial for ensuring an effective grounding system. Always consult with a qualified electrician and adhere to all applicable codes and regulations when installing or modifying electrical systems. Safety should always be the top priority when working with electricity.